Unit 8 is all about chemical reactions, and specifically what we're going to focus on is stoichiometry. But first, let's do a quick review. So the first thing we're going to talk about are physical changes. Physical changes is when you have a chemical equation and the chemical equation does not change. Your chemical composition does not change. All you're doing is going from liquid to gas. As an example for water, you notice that nothing is changing in the chemical composition. Only thing changing is the physical state. So you're not creating something new. The next thing we're going to talk about are chemical changes. In chemical changes, you are always going to have something new. So you're always going to be changing a composition. Endothermic reactions are going to be when you have something that absorbs energy and you go from a low energy and your products end up having a high. So it absorbs the energy. That's why it goes from low to high. And it's cold to the touch. Exothermic is when you start off at a high energy, and when the reaction occurs, it releases the energy and the products are at a lower energy and it's hot to the touch. So here are some examples of endothermic and exothermic processes that you would find in real life. Now we're going to focus really on chemical reactions and the equations especially. And the first thing we need to remember is the law of conservation of mass. However much you started with is how much you end with. So mass is neither created nor is it destroyed in a chemical reaction. That means whatever you start with, the number of atoms, you must end with the same number of atoms at the end. And so in a chemical formula, chemical formulas represent the number of atoms in each element, and you can determine how many atoms you start with in your chemical equation by looking at the elements in a chemical formula. Okay. Chemical equations have chemical formulas, and chemical equations are represented by symbols such as delta for heat, plus for reacting with, etc. Formulas and relative amounts. So the amounts are number of moles of reactants and products within a chemical reaction. A reactant is the substance that reacts in the chemical reaction, and the products are what are produced or what are formed. And so if you remember, reactants are always going to be on the left side, and the products are going to be always on the right side. Now, here are the symbols that you will see in a chemical equation. Plus is when you're adding two reactants or more, or if you produce more than one product. The arrow separates the reactants from the product and also indicates the word yield in a sentence. This tells you, these last four tells you the state. So S is for solid, L is for liquid, G is for gas, and AQ means that you have a solid that was dissolved in water. So it's an aqueous solution. And so here is an example of one of those chemical equations with the correct symbols. All right, so let's go ahead and talk about stoichiometry and how all of these play a role in stoichiometry. So first and foremost, stoichiometry is a calculation of quantities of reactants and products in a chemical reaction. The most important part of using stoichiometry is that you can actually make predictions. This is the point of stoichiometry, is that you can predict how much you're going to make of a product. Or if you have a product, you can calculate how much of the reactants you started off with or you used in the reaction. And when you are doing stoichiometry, the key thing here is having a correctly balanced equation. If you do not have a balanced equation, your stoichiometry calculations will be wrong. So why is stoichiometry important again? Well, it's basically we can go ahead and make predictions without actually having to do the laboratory itself. So there are steps in doing calculations for stoichiometry, and the steps are: one, you have to have the chemical reaction; two, balance the chemical reaction equation; and three, we can do the stoichiometry calculations. And one of the most important things in the stoichiometry calculation, balance equation you need to know is the mole ratio. The mole ratio will tell you whether you have a 1-to-1 or a 2-to-1 ratio between the two chemical formulas that you are comparing. So let's go ahead and start talking about the first step in doing stoichiometry. But before we do that, my bad, we actually have to know certain terms. The first term is mass. Mass is always in grams. If you see kilograms, nanograms, you have to do a conversion. Amount means moles. And the coefficients. Now, coefficients are found in the chemical equation. They're typically the number in front of a chemical formula. So, for example, here's H2O. That 2 is going to be the coefficient for that element, or sorry, for that compound. So let's go ahead and start by talking about how to do a mole to mole conversion. So when you do a mole to mole conversion, you need to know the mole ratio. Okay, the mole ratio is based from the balance coefficient, okay, which I just showed you on the last slide. And so we're going to have to go ahead and use that mole ratio in order to do a conversion. So here's our first example. It states here that using the equation below, if there are 2 moles of MgCl2, how many moles of KCl are produced? Okay, so now that we've looked at the problem, we've looked at the chemical equation, the first thing we need to make sure is that we have a balanced equation. Looking at this, I know we don't have a balanced equation, so I'm going to have to actually balance it. So when I do that, I'm going to put a 2 in front of here, a 2 in front of here. And because these are just one, I'm going to go ahead and just put 1 so that we know that there's a number in front of these. Okay? The next thing I'm going to do is I'm going to go ahead and circle the 2 chemical products and reactant we're going to be comparing. So it says here we're going to compare MgCl2 and compare how many moles we're expecting to produce. So we know in the problem it states that we are starting off with 2 moles of MgCl2. Okay, I'm going to go ahead and put this over 1. We know that for every 1 MgCl2, we produce 2 KCl's. So when we're doing these types of problems, I'm going to go ahead and multiply this by the mole ratio. The ratio that goes on, the number that goes on the bottom, the one that goes on the bottom is always going to be what you started with. So I started off with MgCl2. That means I have to have the moles of MgCl2 down here. And the coefficient for that is 1. Okay? Now, I'm going to put the other number that we had over here for KCl, and we're going to put that on the top because this is what we're trying to find out how much we made of. And so these units cancel out, and I'm left with the units mole KCl. And that means and then I just multiply out the numbers, which means I have 4 moles of KCl. Okay. Here in this next problem, we're going to do another one where it states that in a spacecraft, the carbon dioxide exhaled by astronauts can be removed by its reaction with lithium hydroxide to produce lithium carbonate and water. How many moles of LiOH, lithium hydroxide, are required to react with 35 moles of CO2, carbon dioxide? So, in this example, we're not looking at a product and a reactant. This time we're looking at 2 reactants, because if we start off with 1, we need to know how much we need to react with that so we can get the precise amount of chemicals we need for the reaction. Okay, so I'm going to go ahead and first figure out if we have a balanced equation. Again, we do not have a balanced equation. Okay, in order for this to work, we need to have 2 lithium hydroxides. And I believe now we are balanced. I'm just going to go ahead and put 1 in every single one of these. Remember, it's really important to have a balanced equation. If you have the balance wrong, you're going to have calculations that are not correct. All right, now that we know our balanced equation, let's go ahead and look at the 2 that we're comparing. The 2 we're comparing is lithium hydroxide and carbon dioxide. According to the problem, we're going to start with 35 moles of CO2, and we want to know how much of the lithium hydroxide we need in order to complete the reaction. So, again, like in the first example, we start off by putting the coefficient of the CO2, what we start with. So CO2 is 1, so I'm going to go ahead and put 1 CO2 on the bottom of this ratio, and then I'm going to go ahead and put the second one, which is 2 LiOH, on the top. Oops. And I'm going to go ahead and cancel out my units, which are the CO2. I'm left with the units of mole, LiOH, and next step is just multiplying out 35 times 2, which is 70 moles LiOH, and this is my answer. 70 moles of lithium hydroxide are required to react with 35 moles of carbon dioxide. I hope this is getting easier as we're going, but the key thing here is you need to know how much you start with. This is just like our starting activities with the s'mores, and hopefully this you can understand where we're getting the moles. So here are some example questions. I'd like you to read and try these problems on your own, and then I would like you to pause here and turn it right back on once you've completed the problems. If you still have questions afterwards, please come in and see me in class. You may hit pause. I hope that you have the same answers as I do. For number 1, you should get 0.600 moles O2. For number 2, you should get 1.17 moles of N2. And if you have any other further questions, please make sure you ask me in class. And here's the final example. Go ahead and pause here and unpause when you're ready to check for your answers. Here is the answer to the first part, where it asks you how many moles of ethylene are required to react with 0.133 moles of water. And here is the answer for part B, where it asks you how many moles of ethyl alcohol will result. All right, if you have any questions, please feel free to ask me in class. Practice the problems that are in your homework packet, and I will see you in class.